and then they were suffocated and then they died. So this is the points are very important. So this is some root are the ventilation air can flow, but then some the root cannot flow the air. It cannot allow the air to flow. So then for this kind of the root, I will give you the thermal resistance. So application I talk about the thermal resistance on the pitch root surface. So that for the roof space, for the ventilated, direction of heat flow can be the up and down. Because the roots are this is slough, so the heat can flow up and down. So up and down heat flow, so the all the resistance values are also given. So this is for the ventilated and another for the non-ventilated space. Another will be the surface resistance. So this surface resistance is mostly depending on the wind velocity. So when there's a heat surface resistance, the surface is subject to the wind. So sometimes wind can be the wind floating, sometimes wind is not floating. So the wind mostly affects the heat radiation from the surface. So that when you consider the surface heat radiation of heat resistance, we also need to consider the air. So that another table, I give you the surface heat resistance. We consider the air. So there will be the stay air or the air with the 3 meter per second, the velocity or 6 meter per second velocity. Most things are happening. So that table I also be given. So basic surface is depending on the wind, so it's subject to the wind. So wind is stay air is the wind is not moving. In this case, if the surface positive horizontal, heat flow is up with the 0.11 resistance, and so for the high emitted surface, that's for the low emitted surface. Then for the heat flow is down, high emitted surface is 0.16 for the resistance, and 0.8 for the low emitted surface, 0.8 for the resistance. And 45 degrees slope, we give in the formula value 25, 2.5 and body gauge. So for the body gauge surface, air can only move into the heat can only flow into the horizontal. For the high emitted surface, our value is 0.12, low emitted surface, our value is 0.3. When the air is moving with the 6 meter per second, so position surface can be the any position, heat flow can also be the any direction, resistance you have to take the 0.03. And so if the air is moving with the 3 meter per second, so any position, any direction, so resistance value is 0.04. So external air is the outside air. Outside air we usually take the 3.5 meter per second for the normal situation. In this case, resistance is 0.04. Sometimes the air is moving faster than the 3.5 meter per second because the sometimes air is higher. In this case, you have to use this formula. I is equal to 1 by AC is equal to 1 by 5 by A plus 4.1 V. V is the air speed. Air speed and meter per second. This is a formula I given you. So now that I will really calculate the heat transfer, how much heat will be transferred into the building. So due to this concept, I start from the concept. I start the thermodynamic principle. Thermodynamics is heat conduction, heat conversion, heat radiation. So I given you and also heat resistance to the heat conduction capability, and also there's our values resistance value to the resistant heat. So this is we can calculate by this formula. Another one is the kind of the structure. Kind of structure means there are two kinds of major structure. One will be the roof and another will be the wall. So for the roof and the wall, we can calculate the heat. So those are the formula. Those formula we want to utilize. So now I will summarize everything and I will solve the typical problem. How the heat will be flowing. So okay, this is the overall heat transfer coefficient. Heat transfer coefficient means how much heat can transfer. So this is the heat transfer coefficient. Heat transfer coefficient is a U. U is the heat transfer coefficient. We can use the symbol U. So this is heat transfer means for we construct the wall can be the outside with the outside air, and then the one layer of the brick, and also the gap layer, and another layer of the brick, and then finally the finishing surface with the masonry wall. So the those walls are construction. We can construct the heat transfer coefficient. So then now we will use it in how the wall is constructed. This is the outside outside of the wall, and this will be the brick. Second layer will be the brick. So brick, and also this is the RFA. RFA means that this is the insulation. So this is reflection of fire. Reflection fire means that some metallic, free metallic layer you can also put under the wall. The reason is any heat can be radiated back. So this is the RFA. RFA means that this is similar to the aluminum foil. When you make it a cookie, you can work with the aluminum foil. So that's thin. But this one is only one side is aluminum, another side is heat exhaustion component. So this is the aluminum foil. The aluminum foil is the RFA. And also this one is the air. Then you put the lining. So this is lining. Lining means that any wall, some house that you construct with the timber. So brick wall and timbers are layer. So this is we call the lining. So this lining you have layer and then also with the inside. So this is a typical construction of the wall. Outside the wall and then go to brick and also the aluminum foil. So this aluminum foil is to prevent the heat. It reflects the heat back to the outside. And then the air, the layer and the lining. Lining may be that construct with the wall, timber wall. So that's construction. So the outside air we can use the R0, it's a resistance R0. Brick resistance is the RB. Aluminum foil will be between this one is the RA, this one will be the RA. So this is both sides are A. And then this one will be the R1. And inside will be the RI. So the Q is equal to 1 by R2 there. So the heat transfer coefficient is equal to the reverse of the resistance. So RT is you have to all the things are series, you have to add all. So RT is 1 by R0 plus RB plus RA plus RA plus R1 plus RI. So this is by this way you can calculate the U. So U value we can calculate. So that all the resistance values are given here. This is the R values are here. So resistance, this is the R. This is R. This is R. And this is the R. So R value depending on the construction. If your wall is a wall construction, this way you can take the R value here. And this is for the roof R value and also surface resistance R value. So the how the roof is constructed, how it constructed, you check it and you find the appropriate R value from the table and you substitute the reflection sheet. Reflection sheet is the insulation, so heat can be the reflection sheet. Dimension. So the flow dimension. So this is for the U value. So this is we use as a U value for the flow. Flow dimension is 100 multiplied 100 meter. The U value is that you can take the 0.099. So 20 multiplied 4, this is 0.795. And 2 multiplied 2, this is 1.791. So this is for the U value for the flow. And then the U value for the concrete slab can also be calculated. So therefore the specific formula, but I don't get this one. We just use the surface, ceiling, and wall, and the floor. So the ceiling, wall, and the floor, they are the main things to calculate the R value. So now I give you a break. So after the break, we will do the solve the problem to calculate the heat transfer. So example U value calculation. So firstly you have to find the resistance. Resistance of the bulk material. Resistance means the resistance of the roof surface resistance you have to determine. You have to find the resistance of the pitch roof on the surface. And also we have to add the order system, and then you have to find that U is equal to 1 by RT. So you have to calculate. So this is for the, so we have to find the U value. So we have to find the resistance on any bulk material. So there will be the plate, glass, wood, glass insulation we calculate, and then we will find the R equal to 1 by K. So this is the first step. So this is the U means that so that overall the heat conduction, so that overall heat transfer coefficient, U has to be calculated. So this is the way to calculate. So how to calculate? According to the formula, U is equal to 1 by RT. So they are the different materials. So different materials, they got a different resistance value. Different resistance value, they also got that we have to use a formula. R equal to 1 by K. So write down the resistance of individual element using the resistance table. So this is the resistance table. So resistance table that you can utilize to calculate the individual resistance. And then you have to sum the individual resistance to find the RT. So you have to find the RT. RT is going to you have to add the all resistance. All resistance, then you can calculate the RT. Then you can calculate the U equal to 1 by RT. So this is the way to calculate the resistance. So basically means that we need to calculate the overall the heat transfer coefficient. The reason is, if you are designing an air conditioning system, you also need to consider how much heat is coming into your home. How much heat transfer into your home, so you have to calculate the heat transfer. So by knowing the total amount of heat coming into your home, then you will be able to design the appropriate air conditioning system, especially the machine capacity. So to calculate the machine capacity, you need to know how much heat really coming into your house. So this is the point of this program I use it. I calculated this program to show that how to calculate the heat flow. So this is the program that find the resistance of any bulk material, find the plate, glass, wood, insulation. So R is equal to 1 by K. So given, so you have to calculate the R. And write down the resistance of individual element using the resistance table. So this table you utilize, and you have to use as individual resistance value. And sum the individual resistance and then find the RT, and U is equal to 1 by RT. So this is that we can calculate. Firstly, we have to calculate. So this is a brick structure outside, and this is brick structure 110 millimeter, and the air gate is 20 millimeter, and this is reflective point. Reflective point, and this is the 100 millimeter gap and the plaster hole, and then the inside air. So this is the structure of the wall. So to calculate the structure of the wall, firstly you have to calculate the outside air. Outside air is the R0. So I put the symbol here. Outside air is the R0. R0 is the outside air, and R3 is the RB here. RB inside air gap. So this is the RFL1. RFL1 is this air gap, and also RFL2. RFL2 is also the air gap, and also the R plus hole. So R plus hole is the RP. So inside air, you can use the RE. So this is the structure of the wall. So outside R0, and the brick wall is the RB plus air. So this is the reflective point. The reflective point means that the reflective point laminated. So this is reflection. So this is one kind of the insulation. So this is the 20 millimeter. So RFL1. This one with the RFL2, and plus double is the RB, and the inside is the RN. So those are all the system value is given. So firstly, we have to calculate the R brick. So brick resistance. So brick resistance can also be calculated. So this is the formula is T brick divided by K brick. So T brick divided by K brick. So we have to calculate brick thickness. Brick thickness is 110 millimeter to 110. into 10 power minus 3 divided by K. K brick is already given 1.15. Then you calculate, so R brick is 0.1 meter square Kelvin per watt. So this is we call the R brick. And also you can also calculate the R plus RP. So this is a dP divided by Kp. So dP is we can calculate the plasma thickness. So plasma thickness is already given. This is a 10 millimeter. This plasma thickness this is for the 10 millimeter. So 10 into 10 power minus 3. And RPA also calculated this RP. So RPA is Kp you have to calculate 0.17. So then by this way you got the 0.06 meter square Kelvin per watt. So we calculated that R plus. Okay, this is for that we only calculate for the two components. One for the brick, another for the plaster. So the brick and the plaster has been calculated. Then we have to calculate the air. So air for the three situation. One will be the outside air. So then the air gap and the inside air. So they are the three air. Outside air, air gap, and the inside air. So the outside air is normally this is a moving air. Outside air we already ever taken the 0.04. Outside air is a moving air, so that you already take the 0.04. So this is the external air here. External air. We can take the resistance is 0.04 meter square K by W. So RO. RO is about 0.04 meter square Kelvin per watt. So this is the RO. RO we can calculate by this equation. So this is we finish the outside air. So then we also have to calculate the inside air. Inside air is a reflective point. So reflective point. So for the lamination is a 20 millimeter surface and 100 millimeter surface. So the 20 millimeter surface reflection point. This one is a the value you have to take it onto the table. Once we have to calculate the reflective point. So this reflective points are resistant. R value is, so this is a 0.38. Because this is a we refer the table. This table is this reflective point is one surface of low emittance. So this is the RFS. RFS is the one surface of the low emittance because this one side is insulation, another side is emission. So this is with the metallic. So this is one surface of the low emittance. So this is the reflective point. So this reflective point, how is constructed? Normally this construction is a vertical position. Position for the wall. It's vertical. So this is vertical construction. So direction of heat flow. Direction of heat flow. So direction of heat flow will be the horizontal. So this is a resistance. Resistance means a meter square Kelvin per watt. So this is resistance. So this resistance we can calculate. This resistance is a 20 millimeter weight or 100 millimeter weight. So this one we can calculate. We call it 20 millimeter, which the value is 0.58, 100 millimeter with 0.61. So this is for the, I have only given you the table. So this table. So this is a refractive point. So this refractive point laminated is one surface is a low emitter. So position is for the wall. Now we are attached on the wall. So the position is a vertical. So position vertical, so the heat flow is a horizontal. This is a vertical, heat will flow horizontal. So 20 meter width is a 0.58, 100 millimeter width is a 0.61. So you see here, this one air gap is a 20 millimeter width, therefore RFL1 is 0.58. Another air gap is a 100 millimeter width, so the RFL2 is 0.61. So we only calculate RFL1 and the RFL2. So this one is we can calculate RFL1, RFL2. You finish the brick from the ball, you finish the outside air, RB we already calculate, RB we already calculated. So those things we have already got it. And another thing you have to go is which one you have to get? You have to get the inside air. So inside air. So for the inside air is a stay air. Stay air, so that this value is 0.12. Because you see here, stay air and vertical construction. Why vertical construction? Heat flow is the horizontal. High emitter heat surface is 0.12. So this is a 0.12. Because the inside air is a stay air. Stay air is inside the building, no air is moving. Inside the building, no air is moving. No air is moving, this means a stay air. Stay air. So what is the position vertical? Direction of heat flow is the horizontal. High emitter surface is 0.12. So we take that 0.12. This means that we can actually for the inside air. So I will not write out this one because I have to use those. I write here. So those times maybe I need to use. So this is an inside air. So inside air means that this air is a stay air. Okay, they are stay air. So their movement. Their movement is will be the here. The wall is a vertical. So position is vertical. The air movement, the direction of heat flow horizontal. Heat flow direction is the horizontal. And then we have to calculate. So our value is at 0.12. R is at 0.12. So then you can calculate R in is 0.12. So those factors we can calculate it. So this is once you get the U, then you can calculate the R. After you can surface area, you multiply, then you can calculate the total heat. because of the laminated point. Laminated point and RFL2. RFL1 and RFL2 are the above meter square Kelvin. this one we will calculate. So this product are outside. They are insulation are outside. The system are metallic, are FL1, are FL2, are insulation, are P and are in. So they are the two things. So firstly we have to calculate the R out. R out. Outside is ever we stay. So resistance is 0.04 meter square Kelvin per watt. So this is the external air. External air is here, already given. The external air is ever 3.5 meter per second. Resistance is 0.04 meter square Kelvin per watt. So R out is 0.04 meter square Kelvin per watt. So this is R out. And R method. R method we can calculate. So R method, how to calculate the R method? So R method is, this is the we can calculate T method divided by T method. Okay, T method. So this is the T method. It's a thickness of the C is 1 millimeter, and the K method. So K of the C is a 47.5. So 1 millimeter divided by 47.5. 1 millimeter is 10 power minus 3 because you convert to the meter, and this is divided by 47.5. So this one you got is 0.00002 meter square Kelvin per watt. So we got the R method. And also RFL1 and RFL2. RFL1 and RFL2 they are slow. 45 degrees. Because you see here, this row is 45 degrees. This row is at 45 degrees. Because at 45 degrees, we have to calculate the air gap. So this is for the down and up. So 45 degrees slow. 45 degrees slow. So high emittance C. So this is the high emittance C and the 45 degrees slope. So this one here. This is what we can calculate for as high emittance. High emittance and 45 degrees. Up is 0.17 and down is at 0.15. Up is at 0.17, down is 0.15. So this is for the, we can calculate, this is for the 45 degrees C, I is 0.7, down is 0.15. So, whether we will select the 20 millimeter or 100 millimeter, there are two things. One is the air gap is a 20 millimeter wedge or 100 millimeter wedge. So which one should be selected? High emittance because of the laminated foil. Laminated foil is a high emittance. High emittance. So both eyes are the high emittance because of this is the laminated foil here. This means that both sides. This is different between this and this one. This is the one side. This one you can utilize the one side low emittance. If you see it this way, this is high emittance. So this is a symbol of the laminated foil. So laminated insulation. If you see that this shape, this is the one side is low emittance. If you see that this one, this is a high emittance. So here is a high emittance. This means that both sides of the lamination. So this is this side and then this side. They are covered with the metallic foil. So one side is the one, only this side is covered with the metallic foil. This one is the insulation. But both sides are covered with the metallic foil. Yes. Because of this one is a approximate structure. This one is you have to assume this is a high emittance. High emittance and a 45 degrees. You see there's a roof structure. Roof structure is 45 degrees. This is a 45 degrees. So because of this one, you have to use a 45 degrees. Up and down. Up and down, you can choose any one. So you can take that 0.17. So I will take that up 0.17. And the width is a 20 millimeter. Because you see here, this width. Here given adjacent to metallic is 20 millimeter. So this is you have to use a 20 millimeter. So this is 20 millimeter. 20 millimeter. So you have to use this R is equal to 0.17. So this is a RFL1 is 0.17. RFL1 0.17. RFL2 also 0.17. We calculate. And our insulation. Our insulation have to be calculated. So this is our insulation. So our insulation you don't need to calculate because it's given at 1.5. Our 1.5 is a bar insulation. So this is already given. Our insulation is already given. This is a R 1.5 bar insulation. Because of this one, our insulation is you can take that value 1.5. Because our insulation already given. In the program, calculate U value for the pitch metal deck room with a reflective white insulation and red ceiling with R 1.5 bar insulation. So because of the R 1.5 bar insulation, our insulation you don't need to calculate. You can utilize the 1.5. And then you also have to calculate the R plus double. R plus double is RB. RB is a TP divided by KP. Okay, so the thickness of the plus double is 13 millimeter. 13 into 10 power minus 3. Divided by KP. So K is 0.17. So by this way you got the R plus double. R plus double is 0.08. You got calculation and then you can calculate R in. Inside air. So inside is the saturation is inside the straight air. Straight air here. Okay, inside the straight air. So inside air the air saturation can be the 0.16 because of the horizontal. Inside is normally this one here. Inside is usually the air move to the here. It move to this way. Okay, the here move to here. So because of this one, inside is straight air and horizontal. So this is we can use a 0.16. So higher value you can take a 0.16. So this is R in is equal to 0.16. Then you can calculate RD. And for the inside air is because this is the difference surface. Surface means that in the on the ceiling that will be alright, but this is for the inside air you can take. So 45 degree slope. 45 degree slope is sorry, this one you can take the 0.11. So 45 degree slope, because the 45 degree slope 0.11. So R is 0.11. Then you can calculate RT. RT is equal to R out plus R metallic plus RFL1 plus RFL2 plus R insulation plus RP plus RN. So those things you have to substitute. You can take the if you take the up, you can also take the full up. So this is up, I also take the up. So up or down, you can take any one. So if you start with the up, you can also take the everything up. If you start with the down, you can take everything down. But normally we calculate two things. Up and down we calculate, and we take the higher value. So then, this is we can calculate here. So R is equal to 0.04. Plus R metallic is 0.00002. RFL1 is 0.17. RFL2 is 0.17. R insulation is 1.5. RP is 0.08. R insulation is 0.11. Then you can calculate the total resistance. So that's our resistance. By this way you can calculate total resistance. And then R after that, 1 by RT is you can calculate the U. So this is how we calculate the insulation for the ceiling. So first problem is the wall, another problem for the ceiling and roof. We calculate the whole over all the heat. So how to calculate? For the roof, this is the roof here. So this is roof. The whole roof area you calculate. So this roof area you can calculate for the both sides. So this is the whole roof you can calculate. So this is the roof here. So this roof is A1 and A2. So total AD is equal to A1 plus A2. So A1 plus A2 you calculate roof area. Yes, I can. So but this one is this area. This area is this is common. So when you see from the top, this area is this is a D. So this is a H1. Okay, so this area, this side. Okay, this side multiplied this side is 2 area. So this area is 2 into T1 H1. So this is total area of the roof you can calculate, and then you can calculate total heat. Total heat flow is equal to U multiply A total. Then you got the total heat flow. So by this way you know that how much you flow into your hole. And similarly, for the wall also you can calculate. This is for your wall. This is wall. Wall you can also calculate. So wall area is a W and the total heat flow. Total heat is equal to U multiply AW. So that's total heat flow. So if it's one side you can keep all the day, so both sides you have to multiply with 4. So by this you can calculate that. So the heat flow into your hole. And then you know that total heat, then you will be able to design an air conditioner. So how many kilowatt air conditioner require, then you can calculate. So by this way we need to, it's important to design the total heat. Because we need to cite the air conditioner side. So the air conditioner side 1 and then this one must be equal. So that you can design the air conditioner. This is why we air conditioner design, we use the air conditioning system design, we use the heat flow. So those heat flows are the important factor. All the heat got the resistance, heat resistance. Heat resistance value, their arrangement, their construction, we take account. So that now this 2 program, we show how to take the heat resistance value, how to arrange it, how to see the table. So like I said, you can calculate total U. After you got the U, you multiply it to the area and you can calculate the heat flow total. And then you will be able to calculate the air conditioner side. Okay, this one we also have to calculate to this R. So this construction, firstly you see the outside. Outside is this outside is this is the R0 and this is the R tie. Tie cable is given to get also the thickness of the tie is 19 millimeter. And also plus also this system. Here we put the reflective point insulation. But under the reflective point is we put a rafter. So by putting the rafter, you can neglect the reflective point insulation because no more reflection. Because if you put the rafter, the rafters are only cover the surface of the reflective point, so it cannot no longer reflect. So this is why that you can neglect. So in this case, RFA is 0. So this kind of saturation, RFA is 0. The reason is, this is a point here, okay, this surface are all the light can be reflect. So you cover this one with this one, so this portions are no longer reflection. So this is why. So this reflection why is put the rafter is under like this. So this group is a like this, reflective point like this, and then you put the rafter like this. So rafter like this, so this one will not reflect. So you can neglect it as well as the RFA. So firstly you have to calculate the R0. R0 is the outside air. So outside air is the polycarbonate formula. This is the air bar 0.04. So R0 is 0.04. So air bar R type. So R type is you have to calculate T divided by K time. So the thickness of the tie will be the 19 millimeter. 19 into 10 power minus 3 plus K 0.81. Then you can calculate the R size. So this R size you can calculate. So this will be the by solving this one, this will be the 0.02. So this is the 0.02. So R size we got. And also the RFA is 0. And also the you have to calculate the R plus root cavity. Root cavity means R root cavity. So this is the root cavity means and this is R root cavity. So R root cavity can also be calculated. This R root cavity is here. How the door is constructed? So this is a low impedance surface and this will be the ventilated space. We assume that the ventilation, so the air that can flow into the roof, so this is a ventilated space. If you assume that the roof is a ventilated space, so in this case you can take the higher value. So ventilated space down is a 1.36, so you can take the higher value. So this becomes the our roof cavity is 1.36. So this 1.36 and the 0.46 you can take. One will be the winter and another will be the summer. For example, if you consider for the summer value, you have to take the power. So this is for the summer value. Up is the winter. So in this case, you can assume up for the winter and then down for the summer. Values are for the winter and the down value are for the summer. So the more important is the summer is more important. Summer is the heat. More heat will flow into the building. Because of this one, the summer you have to calculate. So summer is a low impedance surface because this one is a plaster foam and a ceiling joint. So because of this one, they are rafter. Rafter is also made of the timber and also the roof cavity. So these roof cavities are ceiling joints. They are also made of the timber. Rafter timber, ceiling joints are timber. Yes, this means that up down means that heat flow. Heat flow means that winter heat flow up because of the solar fading. Inside heat will go outside. Is the heat up. Summer outside heat go down. So here down like this. That means that inside all the home temperature is greater than the outside, so the all heat in the home will go up. So the from here, summer is winter with the heat go down. Go up. But during the summer time, inside is cooler, outside is hotter. So heat go inside. And now we can assume like this. So because of this one, for the summer time, we take the down. So the 1.36 we calculate. So root cavity 1.36. Another thing is that we have to select whether this is a heat impedance surface. This is low impedance. Because according to the construction, you see here, these rafter are made of the timber, ceiling joints are also made of the timber. So timber, their heat impedance is very low. So because of this one, low heat impedance surface, and so ventilated space for the summer type consideration, so we have to take the 1.36. So the R root cavity is 1.36. Then you can also calculate the R plus star. So R plus star is you can calculate T plus star and it's divided by K plus star. So the T plus star we can also calculate. T plus star will be the star. So plus star both thickness is 13 millimeter, 13 into 10 power minus 3. And K plus star is 0.17. So this one we can calculate, so we can calculate the R plus star. So R plus star is, you got the thing is at 0.08. And also the Rn. So inside resistance you can calculate. So inside resistance is a stay air. Because of stay air, so you can find the thing, so stay air. So normally it's heat flow. Heat flow is down, so you can take for this 0.16 because the heat, summer time, heat flow inside. So tau, so you get to take the 0.16. This is a summer. So this is a tau, heat flow. This means, this is how, this is sun. So heat cool down, so this is tau. Heat flow is tau. So because of this one summer time, you can take the 0.16. Then you can calculate all R2 there. R2 there is equal to R0 plus R tie plus R plus R root cavity plus R plus plus R in. So you substitute. R0 is at 0.04. R tie is at 0.02. RF is 0. R root cavity is 1.36. R plus is 0.08. And R in is at 0.16. So by solving this one, you got the total R2 there. So this total R2 there, so this becomes 1/66. Then so you can calculate U. So this becomes 1/66. Then you can calculate U. So U is equal to 1/R2 there. So 1/1.66. So you got it 0.6 watt per meter square Kelvin. So we got. So this is the heat flow calculation. So today the is heat transfer characteristic. So we calculate that for the air conditioning system design, we need to consider how the heat is flowing. So the approximately those are my 3 examples. You can see that how heat is flowing. So the structure of the material, they are the conductance properties, they are heat resistance, the capacity, they influence the heat transfer. So depending on the structure, so depending on the weather situation, depending on the construction, the heat are there will transfer into the house. So first thing you have to calculate, know is that when you calculate for the particular roof or the particular building structure, first thing you have to sketch. You have to sketch what kind of materials are included. Okay, for the roof, what material, for the wall, how many brick layer, and then you have to calculate the R value for the individual material. So I give you the table. Those tables are the typical table we really use it in the field. So those tables are you can use the brick or the insulation or the timber structure. You can calculate the RV. And also the roof, we also show the example. Roofs are normally we assume that 45 degrees. The sound roof is 22.5. So 22.5 and 45 is the average standard one. So we also calculate for the RV for the roof. And then depending on the saturation, we take out the appropriate value and we add the R value. And then you can calculate U. After you got the U value, you multiply with the whole area. So for the wall, you can calculate the wall area. Roof, you can calculate the roof area and multiply. So you got the heat flow in your building. So this heat flow is that you see that now environmental side, the air ventilation into the roof greatly reduce heat transfer. So because of this one, if you design a modern system, so wind should be allowed into. But in the meantime, you should also prevent the appropriate system to prevent the moisture or the water. So 2 things. Prevent the water and allow the wind. So 2 things have to be designed. This is the architecture design that they can make the modern design system. So we can design to by this way you can reduce the heat. So if you reduce the heat, so the reason these are federal government insulation scheme is that normally all the houses are very hot when the summer time. Very hot, so people use the air conditioning. People use the air conditioning to make more power taken so that it affects the grid. So air conditioning, more electrical power, more gas has to be, more the coal has to be fired, so more greenhouse gas are coming out. This is why they make the roof insulation. So roof insulation, but this case unfortunately they will do the phase out. Phase out means that many treatments that they saw some products that lose a jaw or something. This is the political issue. But in the technically, this is the goal and intention is to reduce the heat transfer amount. unfortunately, that 3 years of practicing, some people cry out and they choke and they die, so 4 people die. So in this case, a lot of the problem happen. So this is the why. So the normal, the real objective is to reduce the heat transfer amount. By reducing the heat transfer amount, you can reduce the use of the air conditioning. So this is the things related. So today I explain that everything. So in the next week, there will be more calculation and also air conditioning design. Air conditioning design is we will take account of the all roof, all the wall, everything, all the building to building, room by room structure calculation will be in the air conditioning design. Okay, that's all for today. So